Here I have a book and I have a map, and I'm gonna put the book horizontal and the map on the book. And when I move the book, the map is following the book. They move together. But if I change the way I move the book, the map starts sliding.
Today we're going to talk about one object sliding on the top of another object. Here we have a box, green box, on the top of the gray plate. Initially they both move together with the velocity v0, and then at some point suddenly the plates start decelerating with a constant acceleration, ap, written here. And when this plate starts accelerating, the box starts sliding on the top of the plate. At the end of the day, both of these objects are going to stop, and we'll find that the box moved distance s on the top of the plate. And we ask 4 questions in this problem. First, find the plate called braking distance. So the assumption that the plate actually has some kind of brakes and it's braking, creating this acceleration. So it's essentially the distance that the plate travels. The next question. There's a friction between the box and the plate. What is that friction coefficient? We would like to know. The third and the fourth questions are about relative motion of the box and the plate. The third question is asking us about the time during which the box relative velocity with respect to plate was increasing. And the fourth question is asking us about maximum relative velocity. Initially, the velocity of the box was the same as velocity of the plate, so the relative velocity was 0. At the end, the relative velocity was also 0. But in the middle, the box was sliding on the plate, and therefore there was non-zero relative velocity. So we should expect that relative velocity would first increase and then decrease. All right, let's start with the first question, plate braking distance, or the distance that plate travels. Well, that's really a kinematics problem. We know the plate moves with constant acceleration ap. So first what we're going to do, we're going to introduce coordinate system. The horizontal coordinate x will be to the right. The origin of this coordinate system will be at the left edge of the plate at the very beginning. And what we find that the coordinate of the left edge of the plate at the end will be that braking distance L. And now we can simply use the formulas we know for the motion with constant acceleration. The formula we know, and I have a link to all these formulas that we normally need. In this case, we're going to use the formula like this. It relates the velocity of an object at any time, velocity of the object at the beginning, acceleration, coordinate of the object at some time, and initial coordinate of the object. So in our case, the first will be final velocity of the plate, which is 0. V0 is initial velocity. A will be our acceleration. And in this case, this A should be equal to minus AP. And it's minus AP because acceleration is in the direction opposite of the coordinate system. Our initial coordinate will be 0. Our final coordinate will be L. And this is the equation we get, and from this equation we can quickly get L, which is 25 meters. Now, the next question is about friction coefficient. Friction coefficient comes from friction force, so we really now need to write down all the forces that act on the box. First of all, it's a gravity force down. We have a normal force from the plate on the box going up. And we have a friction force going back to the left. Notice that the box doesn't move up or down. It means that in magnitude, normal force and gravity force should be the same. N is the magnitude of normal force, m is the mass of the box, and g is gravitational acceleration. On the other hand, we know that horizontally we have only friction force, and that friction force in magnitude should be mu coefficient of friction that we need to find times the magnitude of a normal force, which is mg. On the other hand, from Newton's second law, we know that forces should be equal mass times acceleration. So there is an acceleration to the left due to friction force, unbalanced friction force, and that acceleration we call AB. Or here we're going to call it magnitude of this acceleration as AB. And if you substitute the friction force in this equation, and then we're going to cancel m, we get formula for acceleration of the box, which equals to mu times g. Since both mu and g are constant, acceleration of the box is constant. And again, we can use the formulas of the constant acceleration to describe the motion of the box. Essentially, what we're going to do now, we're going to use the same formula like we used for the plate. The only difference going to be here is that instead of AP, we're going to put AB. And instead of L, we're going to use the distance the box travel, and that distance is L plus this distance S. And since AB is mu g, we can substitute there. And now what we find here, the only unknown here is mu, which we can express from this formula and get the answer. To get the quantitative answer, I use the fact that g was 10 meters per second square, and that's actually what the problem asked us to do. All right, so we answered 2 out of 4 questions. Now let's talk about the last 2. To answer those questions, we need to look at the velocities of the box and the plate. Since both of them are moving with a constant acceleration, but different acceleration, again, we can use the formula that relates velocity with the time. And that's the equation for the box, and this is the equation for the plate. The only difference is we have AB or AP. Now let's draw the velocity of the box and velocity of the plate as a function of time. Notice that V0 and acceleration are constants, so this is actually a linear function. So if we have v versus t, this gray line will be velocity of the plate. Now velocity of the box, we're going to be similar. The only difference is AB in absolute value is actually less than AP, so it's going to be a shallow slope. But now the question is, what is the relative velocity of box and plate? And the answer is, it's actually the difference between the green line and the gray line. And for different time point, the difference is going to be different. Notice at the very beginning it's 0, then it starts increasing until this point when the plate stops. And after that, it is decreasing. So essentially, if you're interested in answering a question about the time during which the relative velocity is increasing, that's going to be this time t. And how do you find it? Well, that's the time when the plate stops. So we're going to use this equation for plate. Vp is 0, small t equals to big T. This is what we get, and this is our final answer. Next question is, what is maximum relative velocity? So that's actually the velocity at the time equal t. So this is the maximum difference between the green and the gray line. So how do we find this? Well, this is the value of the velocity of the box at the time t. So just plug it here. Now we're going to substitute this expression for t. We're going to substitute this expression for VB. And if we do, this is our answer. So we really answer all 4 questions. But now I would like to ask you a question. If you go back to the beginning of this video, you saw me moving a book and I had a map on the top. And sometimes, depending how I move my book, the map would move with the book. So the relative velocity of the map with respect to the book was 0. They go together. And sometimes the map would slide. My question to you, can you derive a criteria when you would expect the map or the object on the top to slide and when the object on the top will follow the object at the bottom?